It's 5 o'clock.
Should be recording.
All right. Mary Lou should be coming to this meeting, right?
I mean,
Should be.
Dr. Kuhn said he might, so I think we just give a few people a few minutes to roll in.
Okay.
Maybe we address some announcements maybe in the meantime. And for the sake of time, I don't know.
Yeah. So yeah, I guess we could start. We'll just get those announcements out of the way. For everybody that's listening right now, we'll also do like a summation email at the end of this, so you can read over that. Kian, do you want to maybe talk about?
Yeah, so as we spoke about last time, we are trying to build Geiger counters this year in ANS so that each of us have our own personal Geiger counter, right, that can detect our relative dose rates and everything. They'd be self-programmable, self-assembled, 3D printed shell casing that easily displays our ISU Bengal pride, right? So really cool thing. I think it'd be a great thing if we all had one as ANS members. They are $100. So what you would do is you would send our treasurer Wesley just an email kind of conveying that you would want one, and then he'll go about collecting payment from you. But we really want to try to get in those orders as soon as possible for the Geiger counters so that we can begin building them as a club together. So that would be cool. But yeah, we'll probably send out another email reinforcing that. So.
Oh, cool. And then you were mentioning there might be a platform called Slack.
Yeah, there is a Slack platform used among other student chapters of ANS that kind of allows the respective chapters to communicate with each other. We don't at ISU believe that we have access to this right quite yet, but we are looking into getting our ANS Slack set up so that we can be more of an interactive club with the whole ANS community. So we're going to look into getting that information out for you guys.
Right, and once we do have that, we'll let you guys know that that's available. And so if you want to network with other students from other universities as well, that is an option that you can pursue. Yeah, and then Patience made another game of Kahoot today, and if you guys want to stick around for that after Dr. Imel's talk, we can play that as well. So, yeah. All right. I'm thinking we may or may not want to wait a little bit longer for Dr. Imel to give his speech over sodium fast reactors. So, all right, Dr. Imel, are you ready?
Well, I have to unmute. Let's see and find my video. Start my video. Okay, can you hear me?
Yep.
All right, let me try to share the screen again. How'd that do?
You're good.
Okay. All right. So thanks for having me here. This is kind of a fun topic for me. So I'm not just going to talk about sodium fast reactors, although it's mostly sodium. But it's a historical survey of fast test reactors. And so I'm going to give a brief introduction to me, very brief. An introduction of this Elsevier project, which is what led me to write this particular chapter. Just a short introduction to that. Then start answering some questions. Why fast reactors? It's not necessarily obvious. Talk about the early years. And by early years, I mean before, well, I guess actually it starts even before I was born. So that's very early years. Then the growth years and then the prototype years. I stop at the commercialization side. I mention it occasionally. So quickly for me, this is, let me just ask a question. You only see my screen, right? The slideshow. Is that correct?
We can also see you too.
Okay. You don't have to see me, but that's okay. Okay. So actually I want to adjust this myself so I don't. Oh, where's my mouse? Oh, well. So after graduate school at Penn State, I've first joined what was then EG&G. It was the site contractor back in the 70s, actually. But I then joined Argonne National Laboratory. Let me try one more time to get rid of that silly thing. I'm going to break out of this for a minute and then, okay, now. Okay. I had to get rid of that annoying participants list on the side. Okay, just the screen?
Oh, you can't see us anymore. Yes, we can just see your screen now.
Yeah, I can't see anybody. I can't see anything. It's a little disconcerting.
You were getting some thumbs up.
Okay, thanks for the verbal. So, I joined Argonne National Laboratory in 1983 after a stint as an assistant professor of nuclear engineering at Penn State. I, quote, retired from Argonne in 2007 to become the chair of NE, recruited by my good friend Michael Lineberry at the time. And I say quotes and retired because I certainly haven't retired. I'm still here. But I didn't actually retire from Argonne. I became a what they call is, what is it called? A senior technical advisor until 2013, actually, until I finally gave that up. But the last 11 years of my Argonne employment were spent attached to CEA in France at the Cataract Laboratory. And so I do have direct experience in 14, maybe 15 experimental reactors on 2 continents where I've actually done experiments on, let's see, 4, 5 in France, 1 in Italy, and then across the United States. So a lot of experimental reactor experience. So what is the project? Well, Elsevier, the publisher, oh no, sorry, is publishing an encyclopedia of nuclear energy. And a subsection of that is titled The Research Reactors. And then a chapter within that is the Historical Survey of Fast Test Reactors. And that's me. That's what this talk is about. Also, in this particular subsection is a historical survey of test reactor programs at the INL over 70 years. And Harold McFarland is going to present this to the NE seminar on November 4th. Now, I don't know if you guys want to somehow tie in ANS to the same way we're doing this or what, but I'm throwing that up just saying that if you like this kind of a talk, historical survey, then Harold's would be really good. He's also a past ANS president, by the way. So the publisher hopes the full issue will be completed in the summer of 2021. And I thought I was late to get my chapter in. I got my chapter in April of this year. And I thought I was late. I was like a month late from what they wanted me to have it in by. I was in plenty of time. So what is the promise? Well, everybody I think knows this. It's virtually unlimited fuel through breeding and fertile blankets. Thorium and U-238 have certainly been the most studied over the years. And the concept was first demonstrated in a usable way in EBR2 at Argonne, and then Phoenix in France was the first. They were the first 2 facilities to demonstrate a breeding ratio of greater than 1. So a quick overview of design differences among the types of fast reactors. There's coolant. Coolants are typically liquid metals for fast reactors. Sodium, lead bismuth eutectics are used. Liquid metals are chosen normally for their low moderation power because we want a fast reactor, so we want a fast neutron spectrum, and then high thermal conductivities. So other candidates have been a sodium-potassium eutectic, it's called NAC, or mercury even was used. Helium or molten salts have also been proposed but sodium has been by far the most common. So another design issue or question is loop or a pool. So this is where we differ from water reactors greatly. We've got a choice here of either doing a loop system where we almost just like a light water reactor, several parallel sodium circuits pump sodium through the core instead of water. A difference now in a sodium cooled reactor because of the reactivity of it, the reactant nature of it, I should say. Each circuit goes to an intermediate heat exchanger, which is still inside the reactor building for safety reasons. It isn't until the intermediate heat exchanger sends the secondary sodium loop outside the building into a steam generator building where the water sodium potential conflict first occurs. So it's out of the reactor building. It's a safer system, but it's expensive because you have to add another major component. But the use of an IHX, intermediate heat exchanger, is common in all types of liquid metal reactors. It's safe but expensive. In the pool reactor, the primary pump and the IHX are contained in a pool of molten coolant of liquid sodium, very big tank. EBR2's case was a big tank of liquid sodium. And the primary then forces the sodium up through the core, and it's discharged over the IHX, and the IHX pulls it in and through and transfers the heat to the secondary loop. That then goes out of the IHX, goes out of the tank itself, and then out of the reactor building to the steam generator building as the other one. So the advantage is inherent heat removal just through conduction. Fuel types, another choice. Isotopic composition, including enrichment. So isotopics are usually plutonium or uranium, or MOX, which is mixed oxide fuel, mixed plutonium oxide, uranium oxide, and mixed together in the same fuel. And then various combinations of those. The structure of the fuel type. Metal fuel has been tested and used. Oxide fuels and even nitride fuels have been used in some test reactors over the years. So the fast reactor, because the efficient cross sections are so much lower, it requires a high enrichment. You've got a higher heavy metal loading in a fast reactor, and that typically leads to higher enrichment requirements. You'll never see a 5% enriched fast reactor. I don't think it would be even feasible to do it, let alone economic. You can do it under 20% though, with new fuel designs. Past reactors, the early ones, usually exceeded 20% enrichment. Some were even 93% enriched. Big advantage in metal fuel and heat transfer. So you've got a direct conduction out of your fuel element directly through the clad to the coolant, and so it's basically if you have sodium bonding inside your fuel element, you've got sodium to clad to sodium, and so it's all conductive heat transfer. Convective heat transfer is a pretty minor component in this one. Metal fuels are also much easier to fabricate. You can cast them because it is a metal, so you use casting technologies. Early reactors did have problems with swelling, which would limit burnup, but they solved that by having an upper plenum in the fuel rod to take fission gas, and that alleviated the swelling problem. So disadvantage of metal fuels, a much lower melting point than the oxides have. So let me break for a minute and pull you guys back. I'm just curious. There, I want to see somebody anyway. Still there? Yep. Okay. It's too disconcerting. I'm gonna leave. Can you see you guys too, the four of you, or just me?
Yeah, we can see on the a right, just like
Yeah.
a list of people's faces and then sometimes names if we don't have cameras.
Okay, let me, if I go to full screen, do you see it then, I wonder?
Yeah, we'll see the faces because that's a separate like function of our zooms. And we're
Yeah.
not seeing you. We're not seeing your view of our faces.
Okay, well, I'll just check in from time to time because I have no, if I lose you, I'll have no way of knowing. No. Okay, I'll just check in from time to time. Okay, so Clementine, or Clementine in French, was actually the world's first plutonium fast reactor. Actually, it was probably the world's first fast reactor, not counting some of the Los Alamos criticals. Construction actually began in 1946 under the direction of Philip Morrison at what was then called Los Alamos Scientific Laboratory. They hated when Congress forced them to change it from that to Los Alamos National Laboratory. They absolutely fought it, but to no avail. They thought scientific laboratory is much more academic sounding. So the reactor name comes from the song My Darling Clementine, which has the line, in a cavern, in a canyon. And so the reactor was constructed in one of the Los Alamos canyons, Pajarita, I think. I'm not sure, but one of the canyons. And so that was one of the reasons for Clementine. And then to Morrison, the workers were like modern 49ers. They were pioneers in exploring something. And then also code 49 is the code for plutonium-239. So 94 protons and then 239. The 9 is the 9 of the 239. So the fuel was plutonium rods clad in steel. The coolant was mercury. It had a natural uranium reflector. The construction was completed in 1949. Operation at a grand total of 25 kilowatts. Now, I'll make a quick note here. The criticality occurred much earlier than the 25 kilowatts occurred, which I can't remember exactly when they achieved the 25. It's in the encyclopedia. But the early criticality was dry critical. That's the advantage of a fast reactor. You don't need a moderator. There is no moderator. And so you can actually go critical with your grid and everything in place, but no coolant system. So typically a fast reactor will start up much sooner, will start up first before it even has any kind of coolant system in. And they can test out their reactor physics designs. It's really kind of cool. That unfortunately, Clementine had several shutdowns due to fuel problems. The last one in 1952 resulted in fuel leaking into the mercury. So they just gave it up and disassembled the reactor. But it did make many cross-section measurements in support of Los Alamos programs, which unfortunately were weapons programs, but we have benefited from all these cross-section measurements of uranium-235 and all the other things we use for nuclear engineering. It also made engineering contributions to the fast reactor program in general, which was just starting. And they discovered that mercury was a terrible coolant. It actually has pretty poor heat transfer properties. So they abandoned the industry. The labs abandoned mercury as a coolant. So we get to EBR-1. So the first criticality of that was in 1951. And that's a historical heritage site of somebody or other, ANS, I guess, at the INL now, which at the time was Argonne West. But it's open in the summertime, generally from Memorial Day to Labor Day. They have trained guides, or you can just do a self-guided tour. It is well worth a visit if you haven't seen it yet. It's your chance to see basically a reactor site with the cooling system, heat generation system, everything in place right there in one building. And then there's a very good mock-up of EBR-2 control room in there too. Anyway, in December that year, they demonstrated the first production of usable electricity from nuclear power by lighting 4 200-watt light bulbs. Now, it also produced enough electricity to power the entire site there where the reactor was located. So it wasn't just 800 watts. But I have to give this parenthetical statement. A lot of people don't know this, that this was technically not the first electricity produced from nuclear power. And that was produced at the graphite reactor in Oak Ridge in 1948, where somebody had the clever idea of a gimmick of hooking up a toy steam engine to light a small Christmas light bulb. And so the steam engine drove a little generator, which then could light a Christmas light bulb. Now, I've always wanted to take our AGN, put some sort of thermoelectric generator or thermoelectric element in the core so we could generate a very small amount of current and light an LED. I'm pretty sure we could do that. So if anybody is interested in a senior project to do that, I think it'd be kind of fun. So EBR-1 was the first reactor to have a complete heat removal loop and electricity generation system, as opposed to the graphite test reactor, which obviously wasn't a usable electricity generation system. The coolant was NAC, that sodium potassium eutectic. Fuel was highly enriched U-235. It was 1.4 megawatts thermal and 200 kilowatts electric, so very small reactor. It operated from 1951 to 1963, was replaced by EBR-2. It did demonstrate a breeding ratio of about 1, which is close to what you can achieve with the uranium fueled reactor. You need to have something like plutonium or U-233 to do better than that. So midway through the core, midway through its that time period, in somewhere around the mid-50s, the core was melted during an experiment. And I was on the reactor safety committee at Argonne for almost my whole career there. I mean, 20 some years. Went through many, many experimental reviews of experiments and so forth. And I don't remember the details of this accident, but it kept coming up as something we can't let this experiment do, like the loss of heat removal tests at EBR-2 and things like that. So, and it was something about, it was confusing labeling of the control rod, and the terminology resulted in the operator adding reactivity instead of lowering it when they were supposed to terminate an experiment. And so it led to the first human factors modifications to a control room way back in the 50s. The core was changed out rather quickly, and they were back up again. So that's something I don't think you could do today. So other early reactors, and we are talking in the 50s now. So in the former Soviet Union, A.J. Lipunsky recognized a little typo there, the favorable neutron balance in a fast system. And that led to the design of the first reactor there, which is called BR5. And it used PuO2, so plutonium oxide, not metal. It did move to nitride fuel in the later years. 5 megawatt thermal loop design. Mission was mostly materials irradiation. Then we get to the growth years. Oh, I wanted to mention that the B, we're going to get Bohr 60 coming up in the reactors, and then there's BN 350 and BN 800 and so forth. The B in a Russian reactor means fast, and it's the word bistro. So a lot of people think bistro is a French, has French origin, you know, the French bistro and that kind of thing. Well, it's actually Russian. It's people in Russia would shout out bistro, bistro if they wanted a faster order to come. And so it caught on, and that's where the term bistro comes from. So starting the growth years now, now we're in the 60s. EBR-2 followed the success of its predecessor, EBR-1. And so its initial design was complete in 1956. Construction began in 1957. Its first dry criticality was 1960, and it went wet critical in 1962, which means the sodium was loaded and the pumps were there and everything. It achieved 30 megawatts, this was thermal, in August of 1964. And the final power level was 62.5 megawatts thermal in September of 1969, where it operated for until 1994. The original mission was to demonstrate breeding, to be a complete power plant, and to operate as a closed fuel cycle. What was called at the time fuel cycle facility got renamed to fuel conditioning facility because recycling was considered a bad word in the years of anti reprocessing. So, but it was constructed to take spent fuel from the reactor, reprocess it, and recast the good stuff back into new fuel pins. That basically morphed into the Integral Fast Reactor program, which, if you haven't gotten a seminar on that yet, you should certainly have one in the near future. So the original phase of the mission to demonstrate breeding was completed. And in the 1970s, then the reactor turned into a fuels and material reactor, including testing for FFTF, which was the fast flux test facility located in Hanford, Washington. Because it was fuels and materials, now the inner blanket, the uranium blanket, was removed and it was changed to a stainless steel reflector. They still kept the outer blanket, but the inner blanket was changed. And then in the 1980s, the mission turned into the demonstration of the IFR concept. And that demonstrated inherent safety tests, the inherent safety of a pool reactor and so forth, which again, you have had seminars or will have seminars on that because it was such an important milestone in our field. It also had a mission of mass tracking and code validation, which I was involved in. I was actually head of reactor physics for EBR2 for about 10 years there in that period. And so we were struggling to really validate our codes so we could calculate precisely where the plutonium is being created and where it ends up in the fuel cycle itself. Big deal for anytime you want to reprocess your fuel. And we wanted to do it on site. That was the whole purpose of the IFR. So the fuel reprocessing and recasting was done in a refurbished FCF, which part of the refurbishing was we had to go in and clean out equipment and decontaminate. And I actually suited up and went inside with outside air supplied like a spaceman. It was spooky. Hot, oh my gosh, so hot. Anyway, the IFR program was terminated by Congress in 1994, and I give a big sob about that. That was a sad day for all of us. So now we move overseas, and we talk about the Dounreay Fast Reactor, DFR. Dounreay, Scotland, it's located way, way northern Scotland. It's up at the very northern tip. Cold, bleak, awful place. No, it's a beautiful place, actually. But it's cold. It's a loop type. EBR2, by the way, was a pool, if I didn't mention it. 60 megawatts thermal, 15 megawatts electrical, very similar to EBR2. First criticality in 1959, very similar to EBR2. Electricity production was from 1962 to its shutdown in 1977. So they were shut down not because they didn't have the mission anymore. They were replaced by the larger PFR, prototype fast reactor, which comes up later. Rhapsody. It's the first step in the French breeder program. Construction began in 1962 and reached its first nominal power level of 20 megawatts thermal in 67. The fuel was MOX, and that's the mixed oxide. The heat was rejected to the atmosphere, so there was no electricity production. It achieved 40 megawatts thermal in 1971, and then operated until 1982. In April of 1994, a fatal explosion occurred while performing cleaning of the residual sodium. C4, Southwest Experimental Fast Oxide Reactor. One loop, MOX fuel, no electricity production. It operated only 3 years, from 1969 to 1972. Had a nickel reflector control system. That's not all that uncommon. ATR has a reflector control system. The mission was primarily to determine physics parameters, particularly Doppler, with regard to safety parameters, and to demonstrate reactor operating characteristics. The site was taken over by the University of Arkansas and used for research purposes. Bore 60 and Joyo. So I just put these together because I didn't have much information about either one. Bore 60 was Russia, or is in Russia, I should say. It's the same order of DFR and EBR2, 60 megawatts thermal, 15 megawatts electric. It's operating, it has been operating since 1967 with Mox fuel. It is still operating today. They are planning to replace it as a materials radiation facility with a new reactor they're building now, but until the new reactor operates, is started up, they will continue to operate Bore 60. And it's served as a materials irradiation facility in support of BN 350 and BN 800. And there's that bistro again. Joyo is also still operating. It's 100 megawatts thermal, operating since 1977. And it's completely as a fuels and materials irradiation facility with Mox fuel. Okay, we're moving along. I'm going to break aside for a second. Actually, I can hear you guys. Can you hear me? Are we still good?
Yeah, we can hear you.
Yep.
Okay. Yeah, I can still. Okay. So we're going to start, the first prototype we're going to start with is Fermi 1. This was designed as a 400 megawatt thermal reactor, but it only achieved 200 megawatts thermal and 60 megawatts electrical of its design limit. It was built and operated by Detroit Edison. It achieved criticality in 1963, but did not produce usable power until 1966. So it took them a while to get the cooling system set up. Within months of startup with a cooling system in place, a zirconium catch plate had broken off, blocking some flow, and that caused the melting of two subassemblies. That's not a good way to start a prototype commercial reactor in 20 miles outside of Detroit. So the accident was investigated. Subassemblies were removed, and the reactor was restarted. So this was the late 60s. After the core reached a burnup in 1972, its burnup limit, it was decided to shut it down permanently. It was to be followed by Clinch River breeder reactor, but that was canceled by Congress in the early 1980s. BN 350, back to the Russian bistro. It's considered the world's first industrial scale breeder built on the shore, and it's built on the shores of the Caspian Sea, which is an aside. That's the site of a Soviet, quote, secret uranium mining center. This is back in the era of the Cold War, right in the heart of the Cold War, the heat of it. I've actually been to BN 350 a number of times. It's an interesting place compared to EBR2, which was spotless, well cared. BN 350 was always a little sloppy looking to me. Anyway, it went critical in 1972 with Mox fuel. It had some startup issues with steam generators, which a lot of them did. And you had to be really careful with steam generators because of the sodium water interface. And so they really couldn't take any chances with their steam generators. But once they got those settled down, it operated about its full power, 650 to 750 megawatts thermal, till about January of 1996. Then they had two more leaks in the steam generators, or leaks in two steam generators, which led them to derate to 420 megawatts thermal. The burnup improved from 9% to better than 12%, so that was very good through materials development. Phoenix, now we're in France. Also a successful prototype. It's a 250 megawatt electric pool type with 3 secondary loops and modular steam generators. Operation commenced in 1973, full power in 1978. Demonstrated a breeding ratio of 1.12 with plutonium oxide. And it operated with a 44% thermal efficiency. And that is typical of sodium-cooled reactors. They can operate at higher coolant temperatures and therefore get much higher efficiencies than light water reactors. Phoenix had the roughly 4 phases of operation from 1974 to 1990, the demonstration of sodium fast breeder reactor technology. From 1990 to 1993, the investigation of reactivity transients. 1994 to 2002, renovation with 2 full operating cycles. And then from 2002, derated to about 350 megawatts thermal until its final shutdown in 2009. It was to be followed by Super Phoenix, but Super Phoenix got canceled. Super Phoenix did operate, but it eventually got canceled by the French government. So PFR, the prototype fast reactor, followed the Dounre fast reactor. So it began operation in 1975. It was designed for 630 megawatts thermal, 250 megawatts electrical. Combination of plutonium and plutonium oxide and uranium oxide fuel, but not MOX, I don't believe. I believe it was just different fuel elements of different materials mixed, whereas it wasn't mixed in one element. So improvements in cladding and plenum design led to burnup increases from 7.5% to better than 15%. I believe in EBR2 at the end of its life, we were starting to approach 22 to 25% burnup, which was a huge achievement. Again, through just better materials, better choice of cladding, better plenum design, etc. So in PFR, its first decade of operation, they were plagued by steam generator leaks, limiting the load factor to 12%, which is terrible. But after 1984, most problems were fixed and the load factor was improved to 57%. It was shut down in 1994. So finishing up fast test reactors, I was asked by the main editor of this book, or this encyclopedia, if I could talk about Russian submarine reactors, even though they're not, they fall outside of the definition of a test reactor, clearly. But we wanted to include them, he did in particular, because of the success with lead bismuth eutectic cooling. The lead bismuth was used by the Soviets from the mid-60s to the mid-90s. And in that period, the Soviets built 12 of these types of reactors and 15 total cores. They accumulated 80 reactor years of operation. So advantages of the eutectic are the very high boiling point. And so one of the issues in sodium-cooled fast reactors is a void coefficient of reactivity. If you void your sodium, because sodium is an absorber in a fast reactor, and there's no moderator, so whereas a water reactor, when you void it, it's going to be a negative temperature coefficient. In a sodium reactor, if you void in the core, it's a positive temperature coefficient. And so you end up with a positive reactivity insertion. If your boiling point is very high, though, you won't have that void problem. So that eliminates one of the problems of sodium reactors. They can operate with a very low excess reactivity because of very low neutron absorption. During their period, they had 3 accidents which rendered the cores useless, but only one was attributed to coolant type, and that was due to the formation of lead oxides accumulating in the coolant, which led to partial blockage. The solution was pretty simple. It was actually better oxygen control in the primary system. So there were no incidents in the last 10 years of operation of these Soviet reactors, submarine reactors. One issue people talk about is the production of polonium-210. But they, after a lot of research, that they found that any transmission of polonium-210 in an accident condition is going to be caused by aerosols. That's the only way to really transmit this stuff because it's so heavy. And so it's mitigated by a rapid solidifying of the eutectic. So if you can get that eutectic cooled down and solidified, and I don't remember what the eutectic temperature is for lead bismuth, but apparently it was something you could prevent that aerosol spread quite easily. So I made a summary table. This is for the encyclopedia of just what all the reactors that were talked about in this particular chapter. With the thermal power, I didn't put electrical power because some of these reactors didn't have any electrical power. The fuel type, and then what its coolant was and whether it was a loop or a pool. So it's kind of handy. You can see the majority of these are definitely sodium loops with a couple, one lead bismuth loop and one mercury loop, and then two pool reactors, EBR2 and Phoenix, two main pool reactors. So, in summary, fast reactors have had a mixed success regarding development as commercial power source. There have been some successful programs, notably EBR2 and BN350. Many had difficult startup periods, like Phoenix and the prototype fast reactor, and quite often with steam generator problems. They've suffered from early cancellations or closures. Closures like, didn't even include Fermi 1 in this list, which was closed early, but then cancellation was Clinch River breeder reactor. Manju is a closure. That's a fast reactor in Japan. It was commercial. It never really operated very well. They had a couple sodium fires there, and then Japan had a number of, or at least one bad criticality incident, and then of course Fukushima came along. So SNR 350 was in Germany. This was a really sad story. I did not visit it, by some of my colleagues at Argonne did. When the construction was completed, and they completed the construction completely, 100%, and they decided to not operate it. And so it was a tremendous waste of money, and also apparently it was pristine, beautiful stainless steel, just awful that they had to close it. And then Super Phoenix in France was a closure due to, well, actually it turned out it was a political coalition between the Green Party and the Socialist Party. The agreement was the Green Party would side with the Socialists against the Conservatives if the government would close Super Phoenix. And it had a lot of problems in the beginning, but they finally got these problems through, and the last couple of cycles ran really pretty well. The French admitted to us when I visited there also that it was much too high a big jump from Phoenix. Super Phoenix was, oh gosh, what the heck was it? It was like 1,500 megawatts of electric, so it was a big jump. Future, not much needed at the present time for a breeder. And so it seems like the future is going to lie in fuels and materials test beds, like the versatile test reactor in the US that's being designed now. And then the one in Russia I had mentioned, the French were going to build Astrid, which was going to be fuels and materials, but I think that project is pretty much dead. And I think that's it.
I have a question for you, Dr. Imel.
Yeah, let me, I assume I don't need my screen anymore. Okay, yes.
Was it Super Phoenix or Phoenix that they had the people that attacked it with an RPG?
I'm sorry. Oh.
Like which reactor was the RPG attacked against?
I don't think they actually attacked it. Did they? I don't think so,
I
Patience.
heard there was a bit where there was someone who tried to
Yeah, they
do
might
something.
have. They might have tried to, and that was probably. I'm going to guess it's probably Phoenix. I mean, Super Phoenix. Phoenix was in basically a classified site. It was pretty protected. I mean, I know Greenpeace has done. They had done some nasty things like hijacking boats that carried fuel and things like that, and they climbed a tower. On the Cataract site, actually, at one of the plutonium processing sites, they actually climbed up the tower and chained themselves up there. But I don't recall of any kind of RPG attack, or actual attack. They might have easily foiled one somewhere.
Dr. Imel, what would you say are the largest challenges for sodium fast reactors going into the future?
Economics. In a nutshell, that's it. We can build them safely. We've demonstrated that with EBR2 is just not to brag about argon, but was just a phenomenal design. The corrosion was never a problem. You could actually still read the weld marks inside the stainless steel tank and the pipes after 40 years of operation. We never had a steam generator leak because it was double walled, and we had detection systems if we did have a leak. So we purposely leaked fuel a lot, but we had a nice system for detection. We wanted to test fuel to its limits and past its limits, so we would actually get breaches on purpose in the tank. And we dealt with all that with no problem at all through the years. So, but economics and also the need were, when I was first getting into this in the early 1980s, my background's actually plasma physics. I was going to work on fusion, which I did for a while, but got disillusioned and went to the fast reactor business because it worked. Fusion is still 50 years in the future. So, but anyway, when I got into this field, we expected to be starting to run out of uranium and certainly oil. I mean, there was no way we were going to have any kind of supply of gas and oil past like 1990, 2000 at the best. And it's just, it seems like, we're awash in gas, natural gas now, and have all the oil we need. And now it is finite. It is going to run out someday. And RU-235 is going to run out too, and maybe someday we'll need a fast reactor. I'll tell you what, Tanner, or if it was Tanner, where was Keen? I don't remember which one. Where was I going? The main advantage where the role of fast reactors is going to come in, besides fuels and materials testing for long lifetime reactors and so forth, is going to be in the area of potentially burning higher actinides. All right, you can use the fast spectrum reactor to burn your americiums, your curiums, your ceriums, your neptuniums, because they are fissionable. They're not particularly fissile. They don't fission with a thermal neutron by any stretch, but they are fissionable. And if you hit them with a fast neutron, I think they will all fission at some point. And so we've looked at a lot of scenarios where we use the fast reactor as a burner for like a fleet of LWRs. And that would then alleviate the waste disposal problem of an LWR. We recognized at Argonne a number of years ago that the fast reactor growth had really ended in terms of research and so forth, that we had to somehow find another mission. And some of the really smart people there realized that this could be something that we could support the fleet of LWRs by helping them address the waste disposal problem. And in the interim, then there would probably be a need for for power production fast reactors by the time you're 40 or 50 or 60 years ago past, 40 or 50 or 60 years past. So that would be the one niche that they could really satisfy.
I've got a question for you.
Okay.
Why were more loop type reactors built instead of pool? And then does it have anything to do with how easy is it to change out instrumentation and stuff if something's wrong, on which one's easier to fix?
Well, there's a conception that the pool type is harder to fix. Misconception, actually, I would say. We would drop subassemblies, we would break things off in the tank and be able to recover them even through opaque sodium. So a lot of our research went into looking at ways to see through sodium in a tank type system, and with limited success, but some success. The you know, I think the answer is probably that the pool type is much more amenable to a metal fuel, because then you got the huge conduction capability, and it leads to the safety, a lot of safety there. You can lose your flow and still transmit your heat out of the core, shutdown heat, but still heat from conduction alone. So you don't need any kind of flow for a long time, days and days. But I've seen a lot of papers and known a lot of people that have worked on the two types of fuels. At Argonne, we were metal fuels advocates because we felt it was easier to cast and easier and had better conductivity properties, heat conduction properties. The French were definitely oxide fuel fans. They felt that the temperature difference, the higher melting point of oxide relative to metal fuel was a huge safety factor for it. We argued that you would never reach those temperatures because you've got such superior conduction, but nonetheless, the feeling was that the oxide fuel worldwide, I think, was the way to go. Even though you can't cast it, and you can't. We were looking for a integral fuel cycle, something that was on site and we could cast and do that, and that really pushed the metal fuel, even not even regarding the safety features. It was an ease of fabrication and so forth. If you take that away and you produce your fuel somewhere else, and then you take it to another facility to reprocess it, it's off-site, then you kind of lose that desire to go that route. So I think it's the fuel type more than the fuel type led to the choice of the pool versus loop. We were big pool fans at Argonne. Okay.
Dr. Imel, I have, well, I was going to ask you if you could make a comment on something. This is Ted. I don't know if it's showing up or not.
Yeah, you're showing us, Ted.
Yeah.
Like you usually do.
Well, see, I've got to get a camera, but I figure the market is kind of slim pickings at this point, so it'll happen sometime down the road. But anyway, so you were kind of, you mentioned a little bit in different parts of questions you were answering about how with IFR you had the integrated part of you're making your fuel right there. You mentioned also with fast reactors how one of the possible or potential advantages would be burning off your actinides from other waste. And I was wondering, could you kind of make a general comment about the necessity for reprocessing in two situations? One is if you're just strictly running a fast reactor fuel cycle, so you're taking that fuel, you want to reprocess. So in that case, but also in the other case of where we kind of are right now, where you have a ton of spent LWR fuel, and you're looking at different issues of, well, how do we get rid of this? What do we want to do with it? And so if we were to somehow utilize that, how does reprocessing fit into that and the sort of crossover to fast reactor fuel cycle?
Yeah, that's a good lead in, Ted. Good question, because again, some of the geniuses at Argonne realized early on that would be something also we could probably address with some of our technology that came out of the fast reactor program, specifically the fuel cycle. And so what the idea was not only would we burn actinides to help the waste disposal problem, but we can also, if we do a reduction of oxide fuel, so we reduce it to take the oxide away, we can then reprocess it in our pyrolytic fuel cycle, which was an electrolysis type of system, electrorefiner it's called, the generic name for the piece of equipment we built. But it's an an electrolysis type phenomena, a reverse battery, where you can separate your actinides and your basically your plutoniums and uraniums from the rest of the junk, but you have to have it in a conducting system. So you've got to get rid of. You can't do it as an oxide. It's going to have to be basically in a metal form of some sort. And so we reduced. They were working on techniques to reduce the oxide fuel, so it could be then reprocessed in the electro-refiner using our technology. So Ted, this would be something that would be built. This would not be part of the integral fast reactor in IFR because it would be not part of the fast reactor cycle itself per se. So it would be a separate fuel reprocessing plant like at La Hague or Le Havre or one like that. So.
Okay, yeah, that sounds good. I mean, that's kind of that's sort of what I included in that paper I'm trying to get published. So that was one of the areas I touched on is well, certain reasons of, well, why would you do this in the first place? And well, here's a reason to do it. So
okay,
I just figured I would make sure I'm still on the right track and get your thought on that.
Okay, no problem.
All right, does anybody else have any questions? All right. Well, thank you, Dr. Imel. That was a really insightful discussion we had there and presentation. Thank you for presenting today.
You're welcome. It was a pleasure.
Thank you.
So everybody stay healthy.
All right.
Anyone really interested in playing Kahoot, or I know we're running a little bit over time. Yeah, I figured.
Okay.
My fault. I'll see you. Bye.
Okay. See you, Dr. Imel.
Bye.
All right. Well, I guess we'll have that as our conclusion to our meeting today. If any of the officers want to say anything else before we end the meeting, you can.
So just a reminder, guys, Dr. Pope is, if you go and sign up to ANS through Dr. Pope, he will be able to get it to where you can sign up for free and essentially get a free membership out of it. I really encourage you guys to do that. At the moment, I don't necessarily know how many students he has had come visit him, but I know that there are more than 2. So help contribute to that number and take advantage of the free membership, because this is a really awesome thing that we have an opportunity to enjoy. So yeah, go ahead and contact Dr. Pope if you hadn't to become an official member.
Hey, Kian, I've been meaning to do that. So I've got to get around to that. I know he's talking about the national membership. Is that also state, or are we just not really bothering with that?
I don't know about the state membership.
Or
but,
what am I thinking of? Yeah, I think in the past we used to do, so you do your national, which I've always done, and I'm not even sure exactly when mine runs up. It's probably really soon, but anyway, the national part, and then there's, yeah, the IANS section, the local section. So are we kind of just forgetting about that?
Yeah, I'll let Tanner answer that.
I actually put IANS's website onto our Facebook page, and it's actually is ians.org. And if you go there, it has a lot of contact information and how to get more involved in the IANS chapter, which would be our local, like, non-student chapter. So if you visit that website, you get a lot more information on that. So, yeah.
You're saying that there's an ISU Facebook page for the ANS or the student chapter?
There is actually, yes.
Okay, so I'm definitely going to look that up, as long as I don't have to be friends with you on Facebook.
Okay,
Just kidding. I think I might already be. I'm not sure, but I have to throw that in.
Okay. Yeah, you can just go visit that, and the website should just be on there. So, yeah.
All right, sounds good. Thank you.
Yep. Thank you. All right, I think that concludes everything. Thank you, everybody, for showing up today.